NASA's Artemis mission is set to be the most ambitious lunar exploration effort since the Apollo era. In collaboration with SpaceX, this mission aims to return humans to the moon and establish a sustainable presence. A key innovation in this endeavor is SpaceX's vertically designed lunar lander, which has the potential to redefine surface operations on the moon. But what will it take for Artemis to succeed? What new technologies are being developed to overcome the challenges of lunar exploration? In this video, we'll dive into the groundbreaking advancements and strategies that could make the moon humanity's next frontier. The vertical lunar lander. A game changer? SpaceX's lunar lander stands out for its unique vertical design, a significant departure from traditional landers used in past missions. This design was chosen for several reasons. First, it maximizes efficiency in terms of space and fuel consumption, which is critical for long-duration missions where every kilogram of payload is carefully calculated. Additionally, the streamlined aerodynamic profile facilitates both descent and ascent in the moon's low-gravity environment. Unlike Earth, the moon lacks an atmosphere to slow down descending spacecraft, making controlled landings especially difficult. However, despite its advantages, the vertical design also presents challenges. Historically, lunar landers, particularly those with vertical configurations, have encountered stability issues. During the Apollo missions, for instance, the lunar module struggled with stability due to the uneven and loose regolith, lunar soil, on the surface. Even in modern times, SpaceX's Starship prototypes have faced setbacks, including crashes and explosions during testing. However, NASA remains confident in SpaceX, largely due to the Starship's reusable design. The ability to reuse spacecraft not only reduces costs but also increases the frequency and flexibility of missions, potentially revolutionizing space travel. Sustainable lunar exploration. Challenges and solutions. The Artemis mission isn't just about reaching the moon, it's about doing so in a sustainable manner. One crucial aspect of this is the development of durable and reusable landing pads. These pads must withstand repeated landings and launches without significant degradation, requiring a thorough understanding of the mechanical properties of lunar regolith, which varies across different regions. The success of Artemis hinges on building infrastructure capable of supporting complex operations. With the Artemis 3 mission approaching, attention is shifting toward whether current innovations will be sufficient to overcome lunar landing challenges. The mission is scheduled for September 2026, but there is a notable risk of delays. Some estimates suggest a nearly 1 in 3 chance of postponement, potentially pushing the mission back to February 2028. These concerns primarily stem from technical challenges associated with SpaceX's Starship lander and the unpredictable nature of the moon's surface. One major risk with vertical landers is their interaction with lunar regolith. The regolith is a layer of loose, fragmented material covering solid bedrock, and its properties vary significantly across different lunar regions. This makes landings particularly difficult, as rocket plumes can displace the regolith, potentially forming craters beneath the spacecraft. This instability could cause the lander to tilt or even topple over if the surface is not adequately prepared. Additionally, high-speed debris ejected from the landing site poses a risk to both the lander and nearby equipment. Mitigating lunar landing risks. To address these challenges, NASA and SpaceX are exploring various strategies. One critical approach is the development of lunar landing pads capable of withstanding the forces generated by rocket plumes. These pads must provide a stable surface to prevent cratering and minimize the amount of debris kicked up during landing. However, constructing such pads on the moon presents significant obstacles due to extreme temperature fluctuations and the lack of an atmosphere, which makes traditional construction methods difficult. Advanced simulation tools are also being used to model how rocket plumes interact with the lunar surface. These simulations help engineers anticipate potential issues and develop solutions before an actual landing takes place. For example, they can guide the selection of landing sites based on the composition and mechanical properties of the regolith. They also aid in refining the design of the lander's engine nozzles and landing gear to reduce surface impact. Further testing and alternative approaches. Another factor influencing Artemis 3's success is the need for additional testing and refinement of the Starship lander. Space exploration is inherently risky, and even well-planned missions can encounter unforeseen obstacles. Recent reports suggest that SpaceX's Starship lander may face delays due to the need for more rigorous testing, particularly under lunar conditions. NASA is also considering contingency plans, including alternative mission profiles in case significant obstacles arise. Beyond these contingency plans, researchers are exploring innovative approaches to enhance lunar landing safety. One promising material is rhino snot, a spray-on polymer originally developed for military applications. This material could be adapted to stabilize dust-prone areas on the Moon by bonding loose regolith particles together, reducing the risk of cratering and debris ejection. Another potential solution is the use of sintered regolith pads, a technique that involves heating the lunar soil until its particles fuse into a solid, durable surface. These pads could withstand the intense forces exerted by rocket plumes, offering increased resistance to erosion and supporting repeated landings without significant degradation. Since sintering can be done using local materials, it presents a sustainable alternative that reduces the need to transport construction materials from Earth. Rethinking lander designs for lunar stability. In addition to material-based solutions, engineers are exploring alternative lander designs to mitigate risks associated with vertical landings. Some concepts propose landing spacecraft horizontally or using multiple smaller thrusters to distribute the landing force more evenly. Horizontal landers could reduce cratering by spreading landing forces over a larger surface area, while multiple thrusters would allow for greater control during descent, enabling more precise landings. While these designs are still in early development, they offer promising solutions for improving lunar landing safety. Additionally, ongoing research into the lunar surface is providing new insights that could further refine landing strategies. By studying the regolith in greater detail, scientists are gaining a deeper understanding of how it interacts with rocket plumes and other forces, an essential step toward designing adaptable landing systems. The future of lunar exploration. Ultimately, the success of Artemis will depend on continued collaboration between NASA, SpaceX, and other industry partners. By investing in cutting-edge technologies, exploring alternative lander designs, and learning from past challenges, these organizations are paving the way for a new era of lunar exploration. Thanks for watching. If you enjoyed this video, be sure to like, share, and subscribe for more updates on space exploration. Let us know in the comments. Do you think SpaceX's vertical lander is the key to lunar success, or could other innovations change the game? This version keeps all the key points but improves readability, flow, and clarity while maintaining an engaging tone. Let me know if you need any tweaks. Rocket.